So this is Math 31, 3.3, rates of change in the natural sciences. This is basically just looking at how can we actually use the derivative in the real world. And I think one of the most important things is that what it does say, find the rate of change of the volume. So rate of change, oops, sorry about that. The rate of change of the volume with respect to the radius. It's important that we attach that meaning behind it, which is dv over dr in Leibniz notation. And then even more specifically, we're going to evaluate dv over dr when r is equal to 10. And that's going to be a really important consideration, that when we look at the function itself, which is that the volume, it is a sphere, so it's 4/3 pi r cubed, the rate at which volume changes as the radius changes isn't constant, because that's not a linear function. So knowing that we're looking at when r is equal to 10 is very, very important in this context. Now to find dv over dr, what I'm going to do is I'm going to take this equation that I've just written, and I'm going to introduce the derivative with respect to r on both sides. And this is why we spend so much time, or at least some time, on implicit differentiation, because this is basically implicit differentiation. When I take d over dr of v on the left-hand side, I am going to have 1, that's the derivative of just the variable, but then I need to include that Leibniz piece, that dv over dr. On the right-hand side, I'm going to bring that 4/3 out front, and the pi, sorry, the constant, and then I'm going to multiply by the derivative of r cubed, which is 3r squared, and I'm going to write it here, that is the rate of change of radius with respect to the rate of change of radius. Now, we talked about this so much in chapter 2 that this is 1, so we don't need to write it. And what we end up getting when we clean up that right-hand side just a little bit is that dv over dr is equal to, so 4/3 pi times 3r squared is 4 pi r squared. The last step here is this is just dv over dr, so that's the general derivative. If we want dv over dr when r is equal to 10, we have to substitute 10 in for r. And we get 4 times pi times 10 squared. 10 squared is 100, so I get 400 pi. Now, something very, very important when we consider these questions are the units. Because the radius is given in centimeters and we're finding dv over dr, the volume will be measured in centimeters cubed, and the radius would be measured in centimeters. Now, certainly over the years, you've learned that centimeters cubed divided by centimeters is centimeters squared, but because of the context of the problem, it's much better to write that as centimeters cubed over centimeters, because that tells us that at a radius of 10 centimeters, if I were to increase the radius by 1 centimeter, I would increase the volume by 400 pi cubic centimeters. Now, that's definitely an approximation, because as even if r was 10.1, this 400 pi would no longer be the rate of change, because if we put 10.1 up here, I would not get 400 pi. So important that that derivative is changing as the value of the function is changing as well. All right, a couple different applications within, and I'll probably split this video into just a couple chunks to make it a little more manageable. As we talk about linear density, if we did want to attach a unit for linear density, typically in that wonderful metric system, we would use kilograms per meter. Very, very important that a lot of the stuff we've talked about previously comes kind of home when we talk about the application. Average density, I just want to write underneath it, is basically a secant line. And then the linear density at a specific point is the tangent line. And it is that idea that with this limit, as delta x approaches 0, we are going from that concept of connecting two distinct points to form a secant line versus finding the slope at a single point, which we would call a tangent line. It doesn't quite connect there, but close enough. Okay, we're going to do that example, and then I think I'll split to another video for the, oh, you know what? We might get them all done, I think, in one. So it says the mass of the left-hand x meters of a rod is given by f of x equals x squared. Try to picture maybe a tapered flagpole or something where, the density of that rod is different as it goes on. That could happen from, heating one end of the rod and not heating the other, or maybe some kind of an alloy change in the middle. There's really kind of endless possibilities of how this could happen. So because it wants to find the average density of the part of the rod given by this interval, we are simply going to use our delta m over delta x when delta x isn't 0. So that's going to be our function evaluated at 2.3 meters minus our function evaluated at 2 meters over 2.3 minus 2. We're going to cheat a little bit in the notes here. The function evaluated at 2.3, I'm just going to write as 2.3 squared. This is the function up here that I'm using. And then I'm going to subtract that function evaluated at 2. And that's going to be over 2.3 minus 2. What that ends up giving me, and I'll round this, it's 4.3. And again, that unit would be kilograms per meter. So that is the average density from 2 to 2.3 meters. Now, in order to find the specific density at, and that's the key conversation here, average density needs to be an interval. Instantaneous or the linear density at a point is just that, a point. So it's not from two x values, it's at one specific x value. And a really good way of looking at that is the dm over dx when x is equal to 2. Now, above, it's written as f of x is equal to x squared, but in this problem, that f of x is the mass of the rod itself. So, in order to find dm over dx, I'm going to take the equation that relates m and x, and I'm going to differentiate that with respect to x on both sides. And what that gives me is the left-hand side just becomes dm over dx because the derivative of m is 1. On the right-hand side, I get 2x. Now, there is that, maybe hidden isn't the right word, but you could write dx over dx there, but you really don't want to because that is going to cancel to yield 1. The rate of change of x with respect to x is always 1. The last part of this then is if I want dm over dx when x is equal to 2, I am simply going to substitute 2 in. And I get that it is 4 kilograms per meter. And that's an important conversation that if I were to use a different x value, we would be very likely to get, and not very likely, but we would get a different density at that point.